All right, let's talk about law of cosines. Law of cosines structurally is a fair amount different than law of sines. Law of sines tends to be a little simpler, straightforward. The calculations are usually quite a bit nicer. But law of cosines can handle something that law of sines cannot. And that issue is that idea of opposite pairs. Notice our cases for law of sines lack either an opposite pair or the ability to create an opposite pair. Like before, you might remember when we had two angles and the side in between them, we weren't given an opposite pair, but because we had the two angles, we could create the opposite pair by finding the angle that adds up to the 100 degrees. We can't do that here with these two side lengths. The only tool we have to find a third side length given 2 right now would be Pythagorean theorem, but Pythagorean theorem requires a right triangle, and this isn't a right triangle. So we don't have the opposite pairs that law of sines would require. Here we don't have any angles, so we don't have any way to get an opposite pair with the tools that we have right now. And essentially, law of cosines solves that problem by generating an opposite piece that we can then use law of sines to keep going on and find anything else that we may want. Also, if we have all the sides and don't have any angles, we can use law of cosines to build one of these opposite angles, and then that would, of course, give us an opposite pair. Law of cosines proof is also fairly different. It requires, or is best done anyway, with a Cartesian coordinate system. So if we put our oblique triangle in a Cartesian coordinate system with that angle alpha in standard position, the nice thing about being in the coordinate system is that we know the x and y coordinates of this point C, because we naturally associate the cosine with the x and the sine with the y. And as soon as we have that x and y as coordinates, we know those lengths. We have that b as the hypotenuse of that kind of larger right triangle. So we have a Pythagorean theorem scenario between b, x, and y. And we have x and y in terms of the b and sine theta, so we can use Pythagorean theorem on those pieces with the x and the y in terms of b cosine theta and b sine theta, and simply simplify that Pythagorean theorem into a nice tool. And I want to take a look for a minute at what this tool essentially does. It's interesting that it's built from Pythagorean theorem, but then once simplified looks like Pythagorean theorem with another piece on it. And it essentially is. Because if you look at a squared equals b squared plus c squared, that looks a lot like Pythagorean theorem, where this is a hypotenuse and those are each legs of a right triangle. But we know Pythagorean theorem doesn't work if it's not a right triangle. Well, what this tool, law of cosines, does, it essentially builds in a check or a fix for the fact that this isn't a right triangle. So a lot of people think of law of cosines as Pythagorean theorem generalized for non-right triangles. And if you think about that, this cosine of theta, if theta was 90 degrees, was a right angle, then the cosine of that 90 degrees would be 0, and this whole term, this kind of check term, would be 0, and you'd just be left with Pythagorean theorem. So in some ways, it's a generalized Pythagorean theorem for non-right triangles. It's a nice way to kind of conceptualize this tool. even though it's built from Pythagorean theorem itself, it's built from Pythagorean theorem around this triangle and essentially builds a modified Pythagorean theorem for our oblique triangle. So we're going to use it in that way. The big important thing here is that, this angle A, we can't think of it as the hypotenuse anymore because it's not a right triangle, so that's not the hypotenuse. It's important that this angle A is the side opposite that angle theta. That those are opposites. So this angle theta and that angle A. So however you end up labeling the particular problem, what the law of cosines is equal to is the square of the side length opposite the angle that you're using. And the B and C are just the other sides. That does bring up something that I think is worth saying. If you have an opposite pair, A and theta, well, if you have an opposite pair, we should be using law of sines. Could you use law of cosines if you had that opposite pair? You could, but then you'd be solving for either B or C inside this, what would be a quadratic in terms of B, and you don't want to be doing that. So while it's technically possible to use law of cosines if you have an opposite pair like that, it's disadvantageous because the law of cosines essentially is a bigger tool than you need. Law of sines will handle it fine. Yes, law of sines has the ambiguity associated with it, and we have to be careful about that. But once you get good at handling that ambiguity, it's certainly worth it for being a comparatively smaller and nicer tool. So let's look at some examples of using this tool for solving for some triangles. Now, you'll see this in a lot of textbooks. It's common. It always kind of irritates me. Thinking of law of cosines as, well, any of these three separate tools kind of just gives you more stuff to memorize. They all say the same thing, as long as, that's C and that's angle C, angle gamma, that's B and that's angle beta, that's A and that's angle alpha. As long as those are opposite pairs, the labeling is really arbitrary. So don't get hung up on the fact that it's got these three different versions. Those three different versions are arbitrary labeling. You've got your side A. This is one of the reasons I like the capitals, the capital letters instead of the Greek. 2BC cosine A. As long as these are an opposite pair, then your tool's going to work. So, labeling aside. So we've got AC and beta here. This is kind of the classic case. Two side lengths and the angle between them. That's our side angle side case. So, again, never hurts to draw a little picture. So we've got angle B at 45 degrees. And notice we don't have side B. We've got side A and side C. And I've labeled them arbitrarily because the labelings really don't matter. So I might have put them in a different place than I usually do. But as long as they're not opposite what we don't want, we're okay. So, again, not to overstress this, we don't have the opposite pair that we'd like for law of sines, so we can't start by using law of sines, but law of cosines builds opposite pairs, so that's what we're going to use. So we're going to label that opposite side B, just to continue with our labeling convention. But the important thing is that that unknown side length is what we're setting ourselves equal to. The other two lengths squared sum, in any order you want, really, minus 2 times the product of your side lengths times the cosine of the angle between them, 45 degrees. Sorry, that got squished there. And then you're just calculating it out. B squared equals, 16 plus 4 minus, 8, 16 times the cosine of 45 degrees. So B squared equals 20 minus 16 cosine 45 degrees. Do be careful. A lot of people are tempted to perform that subtraction. We know this multiplication has to happen first, but sometimes we get tempted to not have that happen when we're doing these problems, because man, wouldn't it be nice to be able to just get a 4 there. So do be careful about that. But 16 times the cosine of 45 degrees, we could get an exact answer there if we wanted to use the square root of 2 over 2, but this is really a decimal approximation type section, so we're going to go with that. So B squared equals 8.7, and don't forget to take the square root there at the end. Now, because we're taking a square root, we do get plus or minus 3.4 when we round. But since we're looking for a triangular length, we're certainly going to go with the positive. But we don't want to ignore the fact that by habit, you do get that plus or minus. Those habits will pay off. So, great. 3.4. Now, the fact that using the law of cosines has built us an opposite pair is great, because now that we have an opposite pair, we can use law of sines. Now, again, law of sines does have a risk that the law of sines can lead to ambiguous cases, but if we're strategic, we can avoid it. The issue with the ambiguous case in law of sines is the fact that we get an acute and an obtuse angle, a quadrant 1 angle and a quadrant 2 angle. And we won't always know which one that we're supposed to use. If we're in a law of sine case, only one of those answers is correct, but we won't necessarily know which one unless we're smart about it. Because this C, that length of 4, is the longest length, we know this angle opposite the 4, this blue one, has to be the largest angle. Well, that means this angle C is the only one that could possibly be obtuse. Maybe it's obtuse, maybe it's not. I don't know. But it's the only one that's possible. The other two have to be acute. You can only have one obtuse angle in a triangle. So while I don't know whether this angle C is acute or obtuse, the angle opposite the 2 has to be acute, because it's opposite the smallest of the sides. So strategically, do not use law of sines to calculate what will be the largest angle if you can avoid it. That way you won't have to worry about the ambiguous case. And that will always be possible in a law of cosines scenario. The only time it's not possible is our angle side-side case that we covered in our law of sines case. So there's no ambiguity, Only one of the answers is possible for C, but because we don't know whether it will be the obtuse answer or the acute answer, it's always better to find the smaller angle first. Now, it doesn't have to be the smallest angle. It could be either the small one or the medium one. We already know the medium one, so that's not going to happen here. But just don't use law of sines to try to find the angle opposite the largest side, and you won't have to worry about law of sines ambiguity. I hope that made sense. So we're going to try to find this angle A first, and then once we know those two angles, finding C will be nice. So if we want to find that angle A, we know the sine of that angle A in ratio to the 2 has to be equal to the sine of the 45 degrees over 3.4, the opposite pair that we just built using law of cosines. So the sine of A equals 2 times the sine of 45 degrees over 3.4. So a little sine inverse, and we'll get our possible answers for A. Notice again I'm saying possible answers because we're going to use sine inverse, so we always get two sets of answers. Sine inverse of 2 times the sine of 45 degrees divided by 3.4, and we'll get, I'm going to say 24.6, and everything coterminal, though we're not going to care about the coterminals. And the other possible answer for angle A would be then what, 155.4 degrees, and everything coterminal to it. But again, we're not going to care about the coterminals because these are triangles. Also, we know it can't be the obtuse angle because we're opposite the smallest side. So, yeah, we get the nice 24.6 degrees. Now you might be thinking, well then why did we do this second part? The same reason you did this plus or minus, which you might not have done, but the same reason I always do this plus or minus with that square root. When we solve using the square root, we generate that plus or minus every time. We ignore it sometimes because we know the context we want the value for. We know it's a triangle, so we know we don't care. When we use sine inverse, similarly, we get two sets of answers. That happens automatically whether we write them down or not. And we reject, in this case, we reject the coterminals because we're looking at triangles. And we reject the obtuse angle because we know we have to be acute. But that doesn't stop it from, when we did the sine inverse, we get two sets of answers. Fair? So try to be disciplined about that, and you'll run into less problems with ambiguous cases. So we know that angle A is 24.6 degrees. We were given that angle B was 45 degrees. So to find angle C, we can just subtract from 180. There's the 24.6 degrees. So it's 180 degrees minus 69.6 degrees. So was that 110.4 degrees? And notice it is obtuse. So if we'd have found C first using law of sines, we'd have gotten what, 79.6 degrees for C if we used the sine inverse, and would have had to have remembered we also got 110.4. And we'd have to choose the obtuse angle for some reason. And it would be hard to justify doing that without finding that smaller angle first. So again, find the big angle either first or last. Don't use law of sines to find the big angle, and you won't have to worry about it. But still respect it. So that's law of cosines. Again, notice law of cosines, its job is to build that opposite pair so we can then use either law of sines or the sum of the angles, use whatever other tools we want based on now knowing that opposite pair. And that's law of cosines. Now here, we're only given side lengths, but that's okay. It'll require a little solving from us, but that's okay. So we're given 9, 6, and 4. And we want to find angles. Well, we got to pick which angle to find, first, second, and third. And again, we kind of want to think about which angle has the risk of being obtuse. The only one that's at risk of being obtuse is angle C. All that means, so it doesn't mean we need to be afraid of angle C. That just means we don't want to use law of sines to find angle C. We either want to use law of cosines to find angle C, so find it first, or use the sum of the angles equaling 180 to find angle C. So find it last, either first or last. Don't use law of sines to find it. Outside of that, you can use any order you want. So we could find either angle A, angle B, or angle C first, just not angle C second. Let's look at what happens if we find it first. Again, it doesn't matter, but let's look at what happens when we find it first. So that means our side length C squared will have to equal A squared plus B squared minus 2AB times the cosine of the angle C. This might be a good excuse to use gamma just because, so I can tell the difference between my C's. It's really the best reason for the Greek. The Roman capital and lowercase c's look the same. But again, you could use W's and V's and J's for all those if you wanted to. As long as this is the side opposite that angle, we're going to be in good shape. So 9 squared equals 4 squared plus 6 squared minus 2 times 4 times 6 times the cosine of the angle we're trying to find. So 81 equals 16 plus 36 minus 8 times 6 is 48 cosine gamma. Just a little bit of solving here. Was that 52 minus 48 cosine gamma? Careful, don't subtract those. It's so tempting, isn't it? Subtract the 52. That's going to be what, 29, I think, equals negative 48 cosine gamma. So negative 29/48 is cosine gamma. Or, however you want to go about simplifying that. So cosine inverse is going to give us gamma. And remember, we will always have two answers because we're using an inverse function. We're going to get two answers plus all the coterminals. That's not cotangent, by the way, it's coterminals. I hope that's not bothering anybody. So cosine inverse of negative 29/48. Well, it's negative, so we know we're going to be in quadrant 2, so we know it's going to be obtuse. So cosine inverse of negative 29/48 is 127 degrees. So 127 degrees. And remember, cosine inverse is between 0 and pi, or 0 and 180 degrees. So the fact that it gave us this obtuse angle is nice, 127 degrees. And cosine's other answer will be down here in quadrant 3, either negative 127 degrees or, 233 degrees. And neither of those can exist inside a triangle. So neither of the 233 or the negative 127. So not only do we ignore the coterminals, we get to ignore that second answer. And this is always the case with law of cosines. Even though we get two answers in all the coterminals every time, just like we did with law of sines, because because cosine inverse will always give us answers in either quadrants 1 and 4 or quadrants 2 and 3, only the principal answer will ever matter in terms of triangles. That's why the law of cosines doesn't give us an ambiguous case. But I really want to stress staying in the habit of getting the full solution. Like, I'm not calculating what the coterminals are, we don't care. But remembering that we get two answers, even if you don't calculate this and you just remember it's there, and the other answer, whatever it is, we're not going to care about it. Being respectful of the fact that we get those two answers, like we're respectful with our plus or minuses when we take square roots, is going to be beneficial for you as you continue on in your studies. So, we have gamma is 127 degrees. Great. We have our big angle, and it did end up being obtuse. Nice. And that gives us an opposite pair. Because we have that gamma at 127 degrees, we now have this opposite pair with the 9. And because we already have the only possible obtuse angle, we can compute either A or B with law of sines with no risk of ambiguity. So, which one do we want to there? Let's do B. So the sine of B in ratio to the 6, its opposite, has to be equal to the sine of gamma, the 127, in ratio to its opposite, 9. So sine B is equal to 6 sine 27 degrees over 9. We could reduce that fraction, but we're just going to sine inverse it anyway. So sine inverse, and sine inverse of 6 sine 127 divided by 9. And that's going to give us 32.2 and 147.8 degrees, plus all the coterminals, But because we know it's got to be the acute angle, we can ignore everything except that nice principle. So great, we have B. So now we know that B is 32.2 degrees. Then angle A, we can simply take the 180 degrees, subtract the 32.2 degrees, subtract the 127 degrees, and get, whatever that is, 180 degrees minus 159 degrees, right? 159.2, I guess. So that's going to be, 20.8 degrees? 20.8 degrees. And it's a nice thing to do at the end of a problem is to check. Largest angle, largest side. Smallest angle, smallest side. Medium angle, medium side. That always has to be true. It's one of the things law of sines teaches us, that ratio always has to be the same. So smallest makes smallest, medium makes medium, largest makes largest. Okay. So we can use it to find angles, we can use it to find side lengths, but generally the law of cosine's job, again, is to build that opposite pair, and then we can use our other tools to find anything and everything else we might need. Ooh. Don't give me trouble. Okay. So some application problems. This tower on the hill problem is classic, by the way. It's a good thing to make sure you practice. So suppose a boat leaves port traveling 10 miles. So it leaves port, from here, okay. Leaves port, travels 10 miles, and turns 20 degrees and travels another 8 miles. So it goes 10 miles in some direction. Like it looks north, but doesn't seem to matter. Turns 20 degrees, so that's 20 degrees. So that means this internal angle there, if we want to think of this as a big triangle, that internal angle would be 160 degrees. And then travels 8 miles. How far from port is the boat? So we want this distance. Okay, well, we've got two lengths and the angle between them. That's what law of cosines wants. And we want the side length opposite this 160 degrees, so that's what law of cosines gives us. So the square of that has to equal the square of the 8 plus the square of the 10. That's what it would be if it was just Pythagorean theorem. But because this isn't a right triangle, we add the check to compensate for the fact that that's a 160 degree angle instead of a 90 degree angle. And again, that's what law of cosines is. And then we just simplify. D squared equals what? 64 plus 100 minus 160 times the cosine of 160. There's a lot of 160s in one problem. So D squared 164 minus 160 times the cosine of 160 degrees. Careful, don't subtract those. Isn't that so tempting? So D squared is, I'm just going to calculate that. You could really just plug the whole thing in if you wanted to. So 164 minus 160 times the cosine of 160 degrees gives us 314.4. Now, of course, that's the square. You know, if that seems really long, it's because square. Always kind of ask yourself, is that number crazy long? Did I remember to do the square root? It's easy to forget. So then D would be plus or minus the square root of the 314.4. So I'm going to square root that whole thing and get 17.7. So it is technically plus or minus 17.7, but we know we want the positive difference, so the positive distance. So we're certainly going to interpret it as the positive 17.7. So, because it's a word problem, you're always answering in sentences. The boat is 17.7 miles from port. I know I'm kind of obsessive about the whole always put the plus or minus, always put the two sets of solutions plus the O-terminals. But the reason I'm so obsessive about that is it really does make a difference. If you're in that habit and then conceptually go, okay, but I'm ignoring those because I know I can, then in the cases where you need them, you won't forget them. So just, you know, be formal, be careful with it, and you'll be better off. Okay. Oh yeah, let's do this one. Sorry. So 134 tower located on a hill. It's inclined at 34 degrees, so it's our 34 degrees of inclination. Oof, let me grab that pen. Let me zoom this in too. All right. So, a couple things to consider. I'm going to draw this in as a solid line here. So a couple things to consider. If this angle is 34 degrees, that means this angle is also 34 degrees. If that angle is 34 degrees, we know this angle has to be its complement, so the rest of the 90 degrees. So that would have to be 56 degrees. Also, if this angle is 34 degrees, then this angle is 34 degrees, which means this big angle has to be 90 plus that 34, so 124 degrees. So that's a big part of this problem, is breaking it down into those pieces. The fact that this is a 56 degree angle, and this is a 113 degree angle, based on this 34 degrees, is fairly pivotal. Where did I get 113? Oh, that was the feet. Sorry. That this is 124. I was going to say, always make sure these add to 180, and 113 didn't work. It's a good check. So finding those based on that 34 degrees is a pivotal part of this problem. We're told that tower is 113. We're told that this guy wire is anchored 98 feet up the hill, and we're asked, we can be asked different things in this one. All right, guy wire be attached top to tower. Find the length of the wire needed. Oh, okay, so we're just trying to find the length of this wire. We could be asked to find all kinds of things. We could be asked to find, how far down the other one would be. We could be asked to find this other length, assuming the angles are consistent. So, we could be asked all kinds of things based on this diagram. So, it's a good diagram to be careful of moving around, or be comfortable moving around, because it's a common type of question. But we want the length of that guy wire. We know these two lengths. We know the angle in between them. So again, it's a classic law of cosines scenario. Two sides and the angle between. So we know the side length opposites square is going to be the sum of the squares of the two lengths minus 2 times the product of the lengths times the cosine of the angle between them by law of cosines. So g squared, we're just going to calculate that. And again, I'm going to try to put that all in nicely. I think it's dangerous to try to do. A lot of people like to just plug it all in all at once. That's dangerous. It's really easy to push the wrong button on something. But, what's 113 squared? I don't know what 113 squared is, so I'm just going to type the whole thing in. Do be careful with your grouping symbols. So get 9,987 well, 8.00 even, so. Feet? That's a lot of feet. Well, that's technically square feet, so. Because this is square feet, that's square feet, this is feet times feet, so this is square feet. That's a ratio, so it just breaks that square feet, so. Don't forget to do that square root. So plus or minus the square root of the 9988. So, and again, I'm just going to square root that exact, or that value as I have it in the calculator, and we get 100. Feet. And of course I'm purposefully ignoring the subtraction or the negative because we know it's a positive length, but I want to respect it when we solve it. So the wire is 100 feet long. Again, don't write your answers like I do, just, reminding you. Answers should be in a sentence. All right, law of cosines. It's a good friend to have. Areas. Let's see, how long do we have? Do I want to do area in a second video? Yeah, let me do area in a second video. So go practice some of this law of cosines stuff, then come back and we'll do area in what I guess is going to be a third video for this week. But that's okay. I'd rather that than have these videos be really long. All right, go practice law of cosines and have a beautiful day.